to point out, because dot products can be negative, this answer can be negative. True? So I just want to be careful and just let you know that that can come out to be a negative value. But if you wanted an image of what it kind of represents, all right. Let's just say this was vector A, right here, and this was vector B. And I'm going to drop 90 degrees here from the tip of B onto A. Now I know this would be all positive, these vectors. But this right here, everyone, this length right here, in this image, would represent component B onto A. Okay? It would give the actual length of this in this image. If you took vector B, took that tip, just thought about dropping 90 degrees, the length from here to here, as you can tell, it wouldn't be quite as long as vector A, but that's what that component would find to be. Well, you have to prove it now, but I bet you everybody in this class could prove that. You know, just using trigonometry and that formula up there, see that dot product? You know what what's cosine of theta and a triangle? So SOHCAHTOA, I bet you could prove that. You could show that. You'd be like, yep, this would come out true. Well, we don't have to do it now. You'd be like, yeah, that's a theta. Cosine theta is what? Adjacent over hypotenuse. You could use this right here to show this, that this length would be represented by that. Cool? But you don't have to do it now. I just want to point that out. So that's called component of B along A, vector B, vector A, almost like a shadow, right? It's like a shadow. That's a scalar. Now there's something also called a vector projection. So a vector projection, they use PROJ, B onto A. And I'll get that formula right over here. What's vector projection, PROJ, B onto A? This is a vector. I don't care if in your notes you drew a, you want to put a big vector, you want to do something like that. This is a vector where this was a scalar. A vector projection is a vector. All right? And you go, what is it? Well, in this case, everyone, it's that vector right here. That's it. That's the vector we're talking about. The component represented its length in that image, but the vector projection would represent the vector that got projected from B onto A, almost like a shadow, as this got projected down that way.
So is the formula the same?
It's almost identical. I'm going to put it in words first. It stems off component. So that's what he means. That was good, Art, that it's like similar. It's very similar. It's going to be equal to this length right here times a unit vector in the direction of A.
Oh.
That's all of it. So I'll put that down. It's just going to be what? This component of B onto A, that number, multiplied to a unit vector in which direction? In the direction of vector, which one? BA, the one that's underneath. Now I put that in words. That's how I remember it. So that you don't have to remember a whole new stinking formula. But can we clean it up and make it look prettier? And then I'll write it over there. Well, what is this then? That's A dot B over what? Magnitude of A? Okay, that's that. That's that number. What's the unit vector in the direction of vector A? We did that yesterday.
That's the.
It was 1 over vector A, magnitude, times vector what?
Yeah.
There you go. So it's all that. There's the answer. This is how I remember it. Take the component multiplied by a unit vector in the direction of vector A. But that's what it is, right? Hey, can you make that even prettier? Yeah, these are the same. So can I just do that squared? So that's how I'm going to write it over here. I'm going to write this as A dot B all over the magnitude of A squared times vector A. You don't have to put the parentheses, but I will. I want that number, that's just a scalar value in front, and then vector A.
Isn't that a vector? A dot B?
Yeah, so I'll put vectors on top of that, thanks. I'll put little arrows. But this right here, Art, is a squared.
Okay.
I thought I would just take that and say, all right, that magnitude, whatever it is, square it. Yeah, let's try that, and when I'm going to draw a picture of one. I got one here. All right. There we go, something like this. Your P, your Q, your R. You're 0, 1, 1. You're 2, 1, 3. You're 5, 3, 1. Can you find this? Can you find that vector? You go, wait a minute, what's B and F? I'm like, oh, I gotta be specific, true? Which one's B, which one's A? So I'm gonna rewrite this as here, I'm like, get this out of the way. How about this? Find vector projection PQ projected onto PR. So I'm gonna write it like that. That little subscript is the one it gets projected onto. Let's find out. Now, first of all, my answer should be just a number or a vector? Good. So in this PROJ, you're like, this will represent a vector again. Right? It's a vector like PQ, it's just got a number in front. There's the formula. There's the formula. So what's this vector A they're talking about? It's this vector PR. What's vector PR?
5.
5 minus 0 is?
5.
5.
Then 2.
2, and then 1 minus 1?
0.
Okay. There's the vector PR. Took care of that. But what goes in front? Dot product over magnitude of
Yes.
which vector squared? So I'm going to dot them, right? Do the dot product. I'll put dot P. What's in the denominator? Which one's squared? This one. So when it said this length squared. So what is the length of
29.
P? Hold on. I just wrote dot product, meaning we're just going to dot them. Let's see what we get. All right, what's the dot product of PQ and PR? Well, I mean vector PQ. That's vector PR. What was vector PQ? What's that vector? Tip minus tail, 2 minus 0? 1 minus 1? 3 minus 1? Is that 2, 0, 2? Yeah? What's the dot product of this and that?
So that's 7.
10 plus 0 plus 0. You all get 10?
Yes.
There's the dot product. Now we need to get the length of PR and then square it. Which really means, if you want, just pull off the radical, right? There you go. So what's 5 squared plus 2 squared?
29. Square root of 29.
Square root of 29 squared becomes just what?
29.
Well, there's the dot product, PQ dot PR. Dot in each two. There's the magnitude of PR squared, radicals off, and then what's vector PR? And you can leave the answer like this unless you want to distribute it. There you go. So it's 10/29. It wasn't the full length. What's that? Now, can you do me a big favor in your notes? Can you draw what this vector would look like? What would this vector look like? Where would it be in this image? It would be the shadow of PQ shadowed onto what?
Here.
I'll do this. It's not that vector. By the way, there is a name for that vector. It's this vector right here. There it is. So I'm just going to put that PROJ PQ onto PR. That's the vector you found. in terms of that image. Probably not showing scale, but that's what it would look like. Just so you know, it's really like, it's like a projection. Like that projector over there. Boom.
So projection is a vector, yeah.
Number 8 from the practice set I'm looking, they just want you to find a vector projection, nothing crazy. That's all right. Before we go into section 12.4, there's one more formula we need to know. But it deals with this again. It's work. Right before your class, teaching Calc 2 was a big topic today. We were finding work on all these different problems. But with us, we're just like, isn't work equal to force times distance? But it's also equal to F dot D. Force vector dot this displacement vector. Okay? So, work is F dot D, but it's also equal to what? Now that we got this, what's another way to write it? I'll put it right underneath it. What's another way to write work? We know work is the dot product between the force and this distance.
So basically like
Magnitude of the what?
Force, magnitude of
Alright,
distance,
magnitude of the force.
magnitude of distance, displacement,
Magnitude of distance, I'll just go like that. And then the cosine of the what?
cosine theta.
The angle between. So on that note, I would like to do a problem like number 10. Now this is in section 12.3. So I'm going to use number 50. Number 10, it was a wheelbarrow. So everyone, I'm going to use number 50, which is a tow truck. I'll put the page on. This is number 50. This is in 12.3. The question, let me read it to you. A tow truck drags a stalled cart along the road. A tow truck drags a stalled car along the road. The chain makes an angle of 30 degrees with the road, and the tension in the chain is 1,500 newtons. Okay, I'm going to draw a picture. Let's see what. 30 degrees there. Here's the car, and the tension is 1,500 newtons. And this truck's just towing this thing, right? How much work is done by the truck in pulling the car a distance of 1 kilometer? So we got to find the work done to pull this truck. There's the tension in the road, and we're going to go a distance of 1 kilometer, which is how many meters?
1,000.
So I'm going to make this 1,000 meters. Just like we were doing today in my Calc 2 class, we write work in either foot-pounds, but if it's in the metric system, with Newton meters, we can just use what? Starts with a J?
Joules.
Joules, yes, we can just write it in joules. So I'll make that 1,000 meters. Let's do it. What's the work done? Work equals F dot D. What was the force?
1,500.
So I'm going to write it this way too. It's the magnitude of F, 1,500 newtons. Magnitude of that distance, that's the length, it was 1,000 meters. 1,000 meters, and what was the angle?
30 degrees.
Cosine of 30. So what's the final answer? 1, 5, 1, 2, 3, 4, 5. What's cosine of 30? Square root of 3 over
2,
2. And I heard the units, just what?
0.
Yeah, I'll put a comma. I'll put a comma. 1.5 million times the square root of 3 over 2. Does 2 go into 1.5 million? Yes, I can at least I can reduce them a little bit.
750,000.
750,000, that'll look a little better. Alright. 750,000 square root 3 J. That's the work necessary to pull that.
These problems are easier than the Calc 2.
I know! Anybody remember work in Calc 2? I spent I think close to an hour. I'm still not done with the lesson. We're like, all right, we did the rope, we did the spring, we did the funny looking circular swimming pool, but tomorrow I gotta do the triangular trough and the pool that looks like when there's a tank that looks like a sphere. Because everything changes in terms of those slices that we gotta sum up. But you're right, it's like, way easier. Okay. Eventually we get to one like number 6, but then when we've done problems like, 7 through 10, we put all those, and now it's time to enter 12.4. 12.4. The cross product. Alright. 12.4 is the cross product. Well, I should leave all that up there, just so you can compare, and I'll put it right here. 12.4 cross product. Okay. What's the cross product of two vectors? A cross B. And I'm going to write this as a matrix. When you do A cross B, you got to think of this as doing the determinant of some matrix. This will always come out to be a vector. So the cross product of two vectors is a vector. Well, let's talk further on that before we start drawing some of these. And I put the definition down how to find it. Let me just use some markers with some little tips on here. So here's two vectors in this plane right here. That's vector A, that's vector B. I put them near each other, but they could be like apart like this. They could be like different here. So in this plane, right? Where is vector A cross B? If this is